all, let me thank the organizers for this invitation. I feel it's a great honor to be giving a talk here, given that I'm actually not a category theorist. So my background is really in representation theory, and I got sucked into this categorification business, so obviously I have to learn something about higher categories, but it's not really my origin. But not really being a category theorist also makes it very difficult for me to judge what the average background of the audience here is. So I've tried. Please feel free to ask questions. There will most likely be things that are unfamiliar for some people. I will try to make it clear when you should take certain things as black boxes or things like that. But yeah, so anyway. So, first of all, I thought I should probably motivate representation theory, given that very unusually for me, this is not a representation theoretic audience. So originally, representation theory came from physics. Yeah, people were studying symmetries of objects and realized that sometimes it didn't matter up to a certain rotation or something, and then so I mean this is where it came from. And then they noticed that symmetries form groups. Yeah, I mean that everybody nowadays learns in their undergraduate course. And they studied how those groups act by commuting elements of a set. And then Frobenius came along, and I would say this is really probably the birth of representation theory, who realized that you can linearize all these actions, and rather than looking at the sets, you can look at the vector spaces spanned by those sets, and look at the group algebra. So you take the group elements as a basis for an algebra, you take the vector space generated by that, you say, well, the basis elements multiply like the elements in the group, and then you extend that linearly. And so that gives you the group algebra, and you have that acting on vector spaces. And this is really what representation theory, where representation theory actually came from. So then there are also in physics and geometrically Lie algebras show up, and people notice they can be studied via their universal enveloping algebras, which are again just associative algebras. So if you take those two things, so one coming from groups, one coming from Lie algebras, but both you study via these algebras, so then people started studying associative algebras just in their own right. Okay? So what is an associative? So I will throughout let K be a field, and so for some of my results later it needs to be algebraically closed. So I'm just going to assume that. Yeah, most of what I'm saying doesn't require that, but I don't want to always put in. I mean, this is sort of more an overview talk rather than everything stated in the most level of generality that I could. So what's an algebra over this field? For the purpose of this conference, and actually for the purpose of my research, it's a k-linear category with one object, or alternatively finitely many objects. That doesn't really matter. Okay. So k-linear means it's a category enriched over vector spaces. And then what's a representation? Well, that's now a k-linear factor from my algebra to vector spaces. Yeah, so if you've seen representations in your mathematical life, then what does this mean? Well, explicitly, I send my one object to the vector space, the module that I'm going to be acting on, and my morphism, my element of the algebra, which is an endomorphism of my one object, I send it to the corresponding matrix or whatever, the corresponding endomorphism of my vector space. Okay? But it's quite important that the point of view that we're taking here is that really an algebra is a k-linear category and a representation is a k-linear functor. To a specific target category which we choose to be vect, and we choose it to be vect precisely because that's the category that our one object category is enriched over. Okay? So this is a short course in representation theory. So now, what is categorification? And here I know even less how much people know about higher categories, whether every category theorist is familiar with n categories, because I'm certainly not. for n higher than 2. But anyway, so categorification is hard to define. Decategorification is just you forget information. So here's a list of examples. So if you have a set, you can forget what sort of elements it has and just remember the number of elements or the cardinality of the set. Or if you have a vector space, you can remember that in linear algebra you learned that if it's over a fixed field, all vector spaces of the same dimension are isomorphic, so they're essentially interchangeable, so you just remember the dimension. Now, obviously you can generalize that, and for a category, you can just forget about morphisms, well, all except for isomorphisms, and you get a set, the set of isomorphism classes of objects. So now suppose you have an additive category, so you have some kind of byproduct on it. Then you can impose on your set of isomorphism classes of objects an operation by saying, well, if I take the direct sum of two objects, I want that to correspond to taking the sum of the isomorphism classes. So that gives you the split Grothendieck group. And now if you have additional structure on your additive category, say it's monoidal, so you have a tensor product, then what you get is, then the tensor product translates into a multiplication on your isomorphism classes of objects, and you get an algebra. Okay? And more generally, if you take an n category, you can produce an n-1 category in this way, in a completely precise way. And categorification is going in the opposite direction, which for obvious reasons is completely non-constructive. Yeah, if I tell you my set have 3 elements, you have no way of guessing what the elements were. So it's not something you can't just sit down and say, okay, I want to find the categorification of something. But you might try to find some categorification. And so why would people want to do this in representation theory? Well, because they observed decategorifications. So if you look at category O of a Lie algebra that deals with Engel functors, which are dealing with finite dimensional representations, and then people observe that these translation functors satisfy the relations of Hecke algebra, and Hecke algebras are completely ubiquitous in representation theory and also physics. So they provide, in physics, they provide solutions to Young-Baxter equations. They are endomorphisms of induced representations for all kinds of groups, finite groups, algebraic groups, depending on what sort of Hecke algebra you take. They are functions, function spaces on certain groups. So Hecke algebras, representation theorists agree, are important. And this is again something where I guess I'll ask you to take as a black box that people care about Hecke algebras in various different areas. And these translation functors, they're functors, but they satisfy the relations of the elements of Hecke algebra. And then similarly, people notice that if you look at certain affine Hecke algebras, then certain induction and restriction functors between them, so there are bigger ones and smaller ones, and you can go up and down, and then they satisfy the relations of a Lie algebra, so these typical Chevalier relations. Yeah? So it's kind of the opposite way around. So in one case, you're acting on something coming from Lie algebras, you have something that looks like a Hecke algebra, and on the other hand, you're acting on something coming from certain Hecke algebras, and you get something that looks like a Lie algebra. And so people were intrigued, and that led to the subject of categorification and representation theories. So why would you want to study these kinds of things? Well, because in the higher structure, you have more information. Yeah, because functors now suddenly have natural transformations between them. In a Hecke algebra, you have elements, and then, well, you can try to multiply them and so on and so forth. If you now suddenly have factors, you can look at, well, what are the morphisms between these functors, and that gives you extra information. So here are some examples of things that have been categorified. So Categorical algebras are more general. I mean, they include finite dimensional Lie algebras, but they also include infinite dimensional ones. They have been categorified independently by Johanna Flauder and Raphael Bouquet. And the motivation for this really came certainly, I think for both, came from topology, because people want four-dimensional topological quantum field theories. And the idea was that you get three-dimensional ones from representations of Lie algebras or of categorical algebras. So maybe if we can upgrade those one categorical level, that will upgrade the dimension of the topological quantum field theory. And so this hasn't quite come to fruition yet, because in order, so three-dimensional topological quantum field theory really come from representations of Lie algebras over, say, rings of cyclotomic integers, and these are categorifications at a generic parameter. Yeah, whatever that may mean. So, so trying to get this is still a very, very hard and open problem. But there's been a lot of progress in that direction. Then other types of Lie algebras have been categorified. Heisenberg algebras, which play an important role in physics. Lie superalgebras, where you suddenly have a Z mod 2Z grading on your Lie algebra. Hall algebras, which come from representation theory of finite dimensional algebras, really quiver algebras. But in certain cases, so they have close links to Lie algebras, the universal enveloping algebras of Lie algebras, and their quantized versions. And then the thing that I want to focus most on in this talk is the categorification of Hecke algebras via Zerbe modules. So this is what came from these sort of translation functors that I talked about earlier. And so people are not just doing this for fun. There's been a lot of progress in representation theory using categorification. So, for example, John and Rouquier proved Rouet's abelian defect group conjecture for symmetric groups. Again, I mean, I'm not going to try to explain what Rouet's abelian defect group conjecture is, but it's a deep, long-standing conjecture in representation theory of finite groups. Yeah? And symmetric groups are very important finite groups because every group embeds in a symmetric group, right? This is something that's, again, usually part of an undergraduate course. So that was a big thing. And then there are these Castellan-Lustig conjectures on Castellan-Lustig polynomials and positivity of constants and so on. They were proved for all Coxeter systems using Zerbe modules by Elias and Williamson in 2013 or 12. I'm quite sure. I learned about it in 2013, but it might have been a year old by then. So this work on Zerbe modules by Elias and Williamson then also led Jody Williamson to give counterexamples to James and Lustig's conjectures, which again were conjectures that people have been trying to prove for ages. And he's also, again in work with others, among them Lustig, been able to give them refinements of Lustig's conjectures that are now thought to maybe hopefully be true. So there has been a lot of progress in representation theory, which is why representation theorists are interested in this. So now how would you kind of go about categorifying something? Yeah, I said it's not really constructive. But in some cases you might get lucky because some algebras, for example, appear as like a Hecke algebra. One incarnation, one of the many incarnations of a Hecke algebra is the convolution algebra of functions on certain spaces. Yeah, so in the most basic example, I take a connected reductive algebraic group. So if that means nothing to you, think about invertible n-by-n matrices. B, a Borel subalgebra. Again, just think about upper triangular matrices. And then, of course, you can look at functions on your whole group that are invariant on each side if you multiply by some element from your upper triangular matrices, from your Borel subalgebra. And that will give you the Hecke algebra. again, one incarnation of it and a special case and so on. And the general philosophy is that the moment you have some functions like this, well, your group has some kind of structure of manifold or algebraic variety, and then you can replace this, so it has some topological structure, you can replace the functions by sheaves. And now sheaves have the major advantage that they have morphisms between them. It doesn't make sense to, if you have functions defined on a set, it doesn't make sense to ask what's the morphism between those functions, but if they're sheaves, then suddenly they have extra categorical structure. And that's a general philosophy. The problem with that is that it's very, very, very difficult to work with. So then people like to try to find some more algebraic descriptions that are easier to manipulate. Because if you really want circle bimodules to view circle bimodules in this case, then they're the monoidal category generated by certain perverse sheaves in the constructible derived category of B cross B by invariant functions on. Yeah. So I mean, not functions. Well, I'm lost in my sentence, but it's very difficult to work with those IC sheaves on the node. So this is where people look for algebraic descriptions. Okay. So now I'm going to, I'll try to define, I'll give the algebraic description of circle bimodules of the categorification of the Hecker algebra later. But first, I want to do some category theoretic background in case the circle bimodule description loses people and they'll be like, oh, this is not interesting. But I figured people should be interested in two categories and two representations. So again, I don't know whether two categories are just the bread and butter of everybody here in the room, but I will define them for those who maybe, and I guess there are probably some PhD students here who maybe haven't absorbed all the canon of category theory yet. So it's a category enriched over the monoidal category of small categories. And when I first saw this in 2008, it meant absolutely nothing. So Eugenia Cheng came to Oxford, where I was a postdoc, and gave a talk, and this was the definition of what does that mean. So explicitly, we have a class of objects. So later, I want it to be a set in most cases, but there are some where I really need a class. And then for every two objects, we want a category, so we have to define morphisms from I to J, and these now form a small category themselves. And the objects in this category we call one morphisms, and the morphisms between the one morphisms are called two morphisms. So that's the terminology I use. I think most people nowadays call them one cells and two cells, but somehow I guess I'm too old for that. I learned it with one morphisms and two morphisms, and I stuck with that. So then, of course, now we have some categories, so our composition that we need, it makes sense to ask for that to be factorial. And again, we need some identities on the categories, so we necessarily, because we already said Cij is a category, every one morphism has an identity two morphism on it, but of course, every object in our category needs an identity one morphism. And then we have some natural axioms that make everything work. And so I've defined the two categories, so I want strict axioms. For the purpose of my talk, it doesn't make a scrap of a difference whether you think two category or bicategory. Everything I'm going to say works for bicategories. Some of it is just slightly more technical if you need to keep track of associators and unitors, but it's not a big deal. So the bimodules, I'm sort of going to give a sort of semi-bi, semi-two category definition. You'll see. So the one example that everybody, even people who are not category theorists, will know is the category of small categories. Yeah, where one morphisms are functors and two morphisms are natural transformations. However, when I first defined a representation of an algebra, I said it's a functor 2, and my target category was vect. So since I want to talk about two representations of two categories, I have to decide what my target category is going to be. And of course, the reason we chose vect was because that was what our algebra category was enriched over. So, the one example that I want to introduce now is going to be the target category of my two representations, because it's the thing that the examples that people have constructed in representation theory, these two categories and the categorifications of the Hecke algebra, the things that those are enriched over. So this is going to be the category AKF. So A is for additive, K is the field, and F is for finitary, because that's in finiteness conditions. So the objects are small, idempotent, complete, K-linear additive categories. So that means they're enriched over vect, they are additive, and for every idempotent endomorphism of my object, I have an object that projects onto. Yeah? And moreover, I want some finite conditions. Namely, so in an additive category, I can talk about indecomposable objects. And I want only finitely many of those up to isomorphism and finite dimensional morphism spaces. So I want to be enriched over finite dimensional vector spaces. And so for representation theorists, the reason why this is the right thing is because this is the kind of thing that you get when you look at the finite dimensional K algebra and you look at the category of finitely generated projective modules. So those are precisely those. So these are the kind of categories that I'm going to represent in, that I'm going to be acting on. And the one morphisms are just functors, but of course I'm additive and K-linear, so I should respect that structure. And then two morphisms are just all natural transformations, as you would expect. So there's no condition on those.
Sorry, can you say what indecomposable means?
Indecomposable means that I can't write it as a direct sum of two things. Okay. Yeah? So if x is equal to y plus z, and x is indecomposable, either y or z has to be 0. I mean, equal, I think. Okay. So now, that's the two categories that I'm going to be representing in. Now, what am I going to be representing? Well, when we started this subject with Walter Mazurczuk in 2010, so the sort of abstract two representation theory, we thought, well, I mean, if you start studying representations of algebras, you might want to start with finite dimensional ones. And not all, but some of the examples that I gave earlier kind of decategorify to something finite dimensional. So we decided on a definition of what it means for a two category to be the analog of a finite dimensional algebra. And this is what we call finitary. So we wanted to have finitely many objects. This is, earlier I said an algebra has only one object, or finitely many, it doesn't really matter. Similarly here, I could in principle get away with one object, but it's somehow a bit nicer to allow finitely many. Then each morphism category is one of the ones that I just described. Yeah? Then composition obviously should respect the structure that I have, K-linearity and additivity in both variables. And then I'm asking for identity one morphisms to be indecomposable. I could omit that and say it just has one object, and I just smear all objects together. But sometimes it's just more helpful. I mean, usually it's more helpful. It gives you extra information if you have lots of, so the idea of this is that I've split my objects up as much as possible. Yeah. Anyway, so that's a finitary category, a finitary two category. And so I already said that the idea is that they should be viewed as two analogs of finite dimensional algebras. And now, most of the the examples showing up in representation theory come from Lie theory in some way. And Lie theory, there are usually some involutions floating around. Yeah, so if you see Lie algebras, so SL2 has an E, an F, and an H, and you can swap the E's and the F, the E and the F. And that works more generally with your Chevalier generators. And similarly, you have an involution on Hecke algebras and so on. And in the categorification, that translates to having adjunctions. And so this is what we simply call a fiat to category. It's a finitary one that has an involution, and this involution leads to adjunctions. So there's a weak involution from C, and I realize this, people call this co-op. I forgot to change this. We traditionally called it op-op because we didn't know about co-op, and I still can't remember which one is co and which one is op, but since I'm taking both, it doesn't matter. So with the usual, so you have these adjunction morphisms, and I didn't write down the adjunction triangle because I figured people here probably know adjunctions, and it's not that important anyway. So that's a fiat to category. Okay, so now let's look at an example, namely the categorification of the Hecke algebra by exemplifying modules. So this is now switching gear a bit. I take a Coxeter group. So what that means is it's a group that's generated by a bunch of elements from a set S, they're called Si, and they all have the property that they have order 2, so they square to the identity. And the only other relation that I have is that for any pair of them, I specify what the order of the product is. Okay? So that kind of group is called a Coxeter group, and they're kind of ubiquitous, like bio groups for Dinkin diagrams, Lie algebras. So I mean, wherever you look, you have bio groups showing up, and those are prime examples of Coxeter groups. Dihedral groups are Coxeter groups. So, and then let B be a reflection representation. So that's say if you have your symmetric group is the Y group is a Y group. Yeah, the symmetric group satisfies this. It's a Coxeter group. You can just let it your symmetric group with n. So on n elements, you can let act on an n-dimensional vector space, yeah, by just commuting these elements. Or actually, yeah. Well, that wasn't quite what I wanted. But anyway, so it's just a certain kind of representation where the SI act as reflections. Yeah, meaning they square to the edges. And it has to be faithful. And so now we define the co-invariant algebra, and this is slightly technical, but if you don't like this, just ignore it. It's just a ring, okay? So what this ring is, I take the basis elements of my vector space, I take polynomials in that, I linearly extend the action on the basis elements to these polynomials. That gives me an action on this C adjoint V. This is called the symmetric algebra on the vector space. And now, of course, I can look at which polynomials are invariant under the whole action. And I can try to kill those, or kill the ideal generated by those. Of course, I have to be slightly careful because the trivial polynomial 1 is certainly invariant. If I kill the ideal generated by all, then my algebra is dead. So I only take those of positive degree. That's the little plus. Yeah. Okay, so this is called the co-invariant algebra. And so a lot of people who actually work with not portioning out by that ideal, like Jody Williams and Ben Elias, they don't kill that. But then you technically don't get anything finitary. It doesn't really matter, but for what I'm saying, but anyway. So now, this is a ring. I can look at modules over it. And in particular, I've killed everything that's invariant under all elements of the Coxeter group. But there will, of course, still be things that are invariant under particular elements. Yeah. So my RSI is everything that's invariant under the action of this one generator, only this one generator. Possibly more, but not necessarily. And now, that's again a ring, and I can tensor R over this smaller ring with R. That'll give me an RR bimodule. Now, oops. So now let me define the category of circle bimodules. This is one object, empty set. So there's a reason for that, because there's an enlarged version, singular bimodules, where you take subsets of your generating set S as objects. And this is just the something where you only have empty set. And we identify that with binarily generated, actually graded projective R modules. So I'm with the grading and so on, I'm lying about the details here, but and now the one morphisms are, in principle, you should just think of them as tensor products of these Ri. Yeah? So what I'm allowed to do is I'm allowed to tensor these up as I like. Then the result might not be indecomposable. Yeah? I might be able to, that might be a direct sum of 15 indecomposables. And then I'm allowed to take every indecomposable direct sum of things that I can get in this way. And then I'm also allowed to take arbitrary direct sums of those. I mean, not arbitrary, finite direct sums of those. So those are the one morphisms, but if you're being very technical, then if you just take bimodules, that gives you a bicategory, and I was talking about two categories, so we stratified, that's the graded. So I'm just looking at endo functors, isomorphic to tensoring and such things. But that's a technical condition, it's not important. And two morphisms are then just, well, if you think of these as endo functors where I tensor with my bimodules, then they're natural transformations, or you can just look at bimodule morphisms. Yeah? So morphisms from one bimodule to another that commute with the R action. So if you're not familiar with rings and bimodules and so on, then take this as a black box, that there is some very algebraic way of defining a two category whose indecomposable one morphisms, so a two category which firstly is fiat, if my bigroup was finite, I meant not bigroup, my Coxeter group was finite, and it categorifies the Hecke algebra. Okay, so if I take the Grothendieck group of that together with my multiple, so my addition that's given by just direct sums, and my multiplication that's induced by tensoring these bimodules, then I get something that categorifies the Hecke algebra. Okay, so now we want to study two representations. And earlier I said a representation of an algebra is a functor from my one object category to vector spaces, and now a two representation, finitary two representation, is in complete analogy just a two functor from my two category to this two category that I defined as my target two category. Yeah, where the objects were those complete k-linear additive categories with finite linearity and so on. Okay, so explicitly that means that essentially I pick some algebra for every object, look at the category of projectives because I said those are precisely these. Yeah. For every one morphism, I now need an additive k-linear functor from one such category to the other. And for every two morphism, I need a natural transformation between those functors. And obviously this all needs to be coherent and needs to satisfy the relations that I did before. So that's a finitary two representation. And the one example that you always want, obviously, is the Unida embedding, which is why your target category where you're representing should always be the thing that you're enriched over. Okay. And the way I defined my Zergo bimodules was actually by some kind of defining representations, right? I said, well, we identify our object with some R modules, and we view our Zergo bimodules as endo-functors that are given by tensoring with these bimodules. Yeah, so this was defined via a 2 representation. And then when you study representation theory for the first time, usually the first kind of representations modules that you study are simple ones. So now the question is, when is a 2 representation simple? And this was actually a bit tricky because so in usual classical representation theory, you have various different descriptions of simple modules. They're the ones that are generated by every element. There are the ones that have no submodules other than the trivial one in themselves. And they're the ones that have no quotients other than the trivial one in themselves. Yeah. And now they all suddenly categorify to different notions. So, but the correct one seems to be the one that doesn't have any quotients. Yeah. Because that gives us a sensible Jordan-Hölder theory.
Sorry.
Yeah.
When you say simple, you mean irreducible? Is it the same thing?
Yeah. That's the same thing. Okay, so I mean the technical condition is that there are no proper C-stable ideals, but what this really means is that I can't meaningfully kill anything without killing everything. Okay, I can't factor anything out without just killing what I have. Okay, and so you can then ask, well, for interesting 2 categories, can we classify simple 2 representations? And this is what people in representation theory set out to do when they started studying the subject. And then once you know your simples, you kind of want to know how you can put them on top of each other to build other representations. But that's sort of a starting point. Okay, so how can we go about doing that? So from now on, curly C will always be a Fiat 2 category. And then one thing that every finitary 2 category actually comes with is a certain cell structure, which comes from the additive structure. So we can define a left partial preorder where we say, so I've called my indecomposable one-morphisms theta with various indices, which sort of are, because I'm later going to apply this to Zergo bimodules, so the indices resemble elements in maybe a constant group, capital W. But in principle, they are just indecomposable one-morphisms. And I say one is less than the other. So something is bigger if I can get it from the thing that it's bigger than by multiplying something from the left. And then it has to appear as a direct amount. Yeah, so I start from theta v. I'm allowed to multiply by something from the left, by some theta u, and then theta w is bigger if it's a direct amount of such a thing. So it's somehow in the left ideal generated by theta v. Okay? And then left cells are just equivalence classes with respect to that. And now, of course, there was no reason why I need to multiply from the left. I can also allow myself to multiply from the right. That gives me the right pre-order and right cells. Or I could say, well, I'm interested in a coarser structure. I'm allowed to multiply from both sides. That gives me 2-sided cells. And then one thing that's quite important for us is now I have left cells and I have right cells, and I can look at intersections between left cells and right cells. And those are called H cells. So this actually comes from very classical, so it's a generalization of stuff that semi-group theorists do. And to these H cells, they can associate simple representations. So this is sort of maybe a bit the motivation behind that. Okay, so this category of Zergo bimodules that I defined, that may have been a bit too algebraic for this audience, but the really important thing about it is that the indecomposable one-morphisms are labeled by elements in the consider group. So that's what I meant by it categorifies the Hecke algebra. And if I look at how they multiply, they satisfy the same relations as elements in a particular cellular basis of the Hecke algebra, which is called the Castellan-Lustig basis, which people have studied, well, since Castellan-Lustig defined them, which was a long time ago. So that means that our cell structure on our two category, because I said every finitary, in particular every Fiat two category has the cell structure. So of course the two category of sorted bimodules has the cell structure. And the cells that we get are precisely the Castellan-Lustig cells coming from the cellular basis that Castellan-Lustig defined. So here's an example. So if you take the dihedral group with 8 elements, that's the Coxeter group of type B2 or C2, those are equal. So then you have your 8 elements, and you have the cell structure is this. So the identity element is its own cell, and that's the smallest cell. Then I have another cell, the longest element is also its own cell. So its own left cell, its own right cell, its own two-sided cell. And the others the other 6 form one big two-sided cell, which splits into 2 left cells. So the columns are left cells, and the rows are right cells. So there's a left cell that consists of everything that has an S at the end. There's a right cell that consists of everything that has a T at the end. And then, of course, you have intersections, which are these single blocks. Those are the H cells. Okay? And in particular, we will focus on what we call diagonal H cells. So there's a reasoning to how they are aligned here. And so a diagonal H cell would, for example, be the one corresponding to consisting of S and STS. So now, if in a general two-category, Fiat two-category, we look at some diagonal H cell, then we can, in multiple steps, which I'm going to just put there but not talk about, construct a much smaller two-category, whose indecomposable one-morphisms are now just going to be the identity, so an identity on a specific object, that's determined by my H cell, and the indecomposable one-morphisms in that H cell. Okay, so how to do this is quite technical, but you can construct a much smaller two-category, which now only has the one-morphisms in that H cell and the identity on the corresponding H cell. So in this example that we just looked at, if we fix this H cell that I pointed out, then we now have something rather than having 8 indecomposable one-morphisms, we have 3. Okay, and the cell structure then is just that. So that's a lot smaller. And then the reason why we're doing this is because we have, if we do this for every, so we have our big, possibly very big two-sided cells. In every two-sided cell, we pick one H cell, which will be much smaller. We look at all these two categories CH that we get in this way, and we look at their simple two representations. Then we get something that's in bijection with all simple two representations of our two category. Yeah? And I've put non-trivial here because otherwise I need to phrase things slightly differently. So non-trivial here just means, so for example, for circle bimodules, what you always have is two representations where the identity on some object acts by the identity functor on vector spaces, and everything else just acts by 0. And those are boring. And we can get them, but I would need to say things slightly differently. So, but yeah, because I would count them multiple times in the second thing. So the non-trivial is really just to simplify notation a bit. But so we can get all simple 2 representations by studying these tiny 2 categories CH for one H cell in every 2-sided cell, and looking at those instead. So we want to concentrate on these CHs because they're much smaller. Yeah. So that's called H cell reduction. And now lustig, for any Coxeter group associated to such a diagonal H cell, something he called the asymptotic algebra. So Hecke algebras involve some parameter Q, which you can send to 0, and then you get something called the asymptotic algebra. And he has essentially the same result that simple representations of Hecke algebra. So this obviously predates ours by a long time. The simple representations of the Hecke algebra. And I should probably have said, this was work with Marco Mackay, Walter Massachusetts, and Joey Jung. I mean, I wrote it there, but I should probably mention their names. So Lustig showed that there's bijection between simple representations of the Hecke algebra and simple representations of the asymptotic algebras, where again, you pick one asymptotic algebra for some H cell in every 2-sided cell. And these asymptotic algebras are much, much easier to understand. So now you would hope that you could combine those 2 things. And indeed, Lustig actually, once Zermel bimodules existed, he similarly associated an asymptotic bicategory to every H cell in Zermel bimodules, which categorifies the asymptotic algebra in the same way that Zermel bimodules categorify the Hecke algebra. And this is actually a fusion category, meaning it's semi-simple, and it's much, much easier to understand than our 2 categories, which are very, very far away from being semi-simple. So being semi-simple meaning everything is a sum of simple objects. And so in particular, so not for all Coxeter groups, but for finite Weil groups, these asymptotic bicategories are very well understood, and people know their simple 2 representations, and so on and so forth. So we would hope that we could relate in a similar way SH to AH. Yeah, so that we could relate the Zermel bimodules to their asymptotic bicategories, which are understood in the same way that we could. That it was done on the decategorified level by Lustig. And of course, the naive hope I told you about H cell reduction would be that CH would just be AH in this case. Yeah, and that's not true. But from now on, let's assume that our Coxeter group is finite. And then we can always construct certain 2 representations, which are called cell 2 representations, which we associate to a left cell. But in our S sub H, the H cell is now its own left cell. Yeah, so that always gives us one simple 2 representation that we can construct, which is essentially you just look at your 2 category acting on the things in that H cell, and you kill as much as you possibly can without killing everything. So that's simple. And then very tautologically, of course, if I have a representation, I can look at its endo-functors that commute with this. There's endomorphism 2 category. And then, of course, because they commute with this, with the action of my 2 category commutes with the action of the endomorphisms. Yeah, so I have this very, very tautological functor from whenever I have something acting, it commutes with its endomorphisms. So I have a functor to the endomorphisms with respect to the endomorphisms. But then in representation theory of finite dimensional algebras, something that plays a big, big role is a double centralizer theorem, which sometimes holds, not always, but which allows you to go back and forth between the thing that acts and the thing and its endomorphisms. And so we can generalize this for any CR2 category, but I'm only stating it for Zermel bimodules here, and any simple 2 representation, that if we look at the endomorphisms with respect to the endomorphisms, we actually just get our elements from our two-sided, our H cell H. Yeah. And I mean, again, this is there are some technical conditions. I don't want to explain what the inch means and so on. But so the idea is we have some analog of this double centralizer theorem, which plays a really big role in representation theory of finite dimensional algebras.
Sorry, can I ask a question?
Yeah.
Is this related to the issue lemma, the one about trivial?
So no. So in some sense, in finite dimensional representation theory, in representation theory of finite dimensional algebras, yes. But here we don't have Schur's lemma. Yeah. So it is. So in fact, most of the time, two representations that are somehow labeled by the same H cell, in the sense of coming from that CH, will have morphisms between them. But it is somehow morally related because the double centralizer theorem for finite dimensional algebras works particularly well when things are semi-simple, and then it is based on Schur's lemma.
Okay.
Yeah.
Thank you so much.
So what this double centralizer theorem allows us to do is to relate the two representations of S sub H to this endomorphism 2 category. And now the proposition that makes everything work is that this endomorphism 2 category is actually our asymptotic bicategory. So if you remember, so this is theorem 2, which follows from the double centralizer theorem, which we proved with Mako, Akai, Waterhauser-Chuk, Daniel Tugendhammer, and Joey Jung, that there is a bijection between the simple representations of using the double centralizer theorem, the simple two representations of the asymptotic bicategories, and the simple two representations of these H cell reductions. Okay, and this is actually a stronger statement that I'm saying. It's not just a bijection, but it's actually an equivalence of two categories. And if you now recall this theorem that allowed us to reduce from the H cell reduction theorem, that allowed us to go from S to all the S sub H's, and now from the S sub H's we can go to the A sub H's. So if we put those together, we get the theorem that we have a bijection between the simple two representations of S and the simple two representations of the A sub H's, these asymptotic bicategories. And as a final remark, is that this actually completes the classification in all finite Coxeter types apart from H3 and H4, which I don't even know the Coxeter groups to that really. But there are a few H cells in those types where the asymptotic bicategories are not understood. So our reduction theorem holds, but people haven't studied the asymptotic bicategories enough. So anyway, that was what I wanted to say. Thank you.
Thank you very much for this lively introduction, not only into categorification of representation theory, but also representation theory per se at the beginning. I really appreciate that. Do we have questions for this meeting? There were questions. Yes, to the right, yes.
Thank you very much for your talk. First, I'd like to just salvage my reputation and say that in that 2008 talk, I didn't just launch in and say that
No, you didn't. It was just, I was a bit...
No, I did.
You did.
A quick question. You said something in passing about the two category, when you constructed the two category observable bimodules, about strictifying it by taking isomorphism classes. And you... Oh, no?
No, so what I was saying is, if you just look at bimodules, they only form bicategory. But if you just view them as if you say we take all endofunctors isomorphic, so I just close under, I view the bimodules as endofunctors of the module category, and I just close under isomorphisms in those endofunctors.
Okay.
Yeah?
Maybe that answers my question, but I think that, yeah, I was just interested in that.
Yeah, no, so in some sense, it's easier to work with two categories. Yeah? And of course, if you have endo functors of a certain category, that's naturally a two category. And so if you now say, well, we have certain bimodules, but we just view them as endo functors of the category given by tensoring with that bimodule. Yes, I have R bimodules. I view them as this bimodule tensored over R black. That's an endo functor of my category of R modules. And now, if I now take everything that's isomorphic to these things, then that's naturally a two category. And it's somehow much, for me, it's a much more intuitive and manageable strictification than taking some abstract thing. Yeah.
Is that not the Omega style that you discussed, right?
Yeah, you could say that, yeah.
There was a question just behind Eugenia, yeah?
This is all good. Yeah, so in ordinary representation theory, say, character theory is a sort of way of decategorifying. So is there a sort of general category theory, so character theory?
So people have looked into this. We had this, you were there, this Traces and Characters Day in Oxford ages ago. But the thing is that the things that we're categorifying are groups, and characters really only make sense for group representation theory. Yeah, so somehow characters are taking it too far because I mean, in classical representation theory, you look at the action on a module, and then for groups it makes a lot of sense to look at at the matrices by which your group elements act and look at the traces. But in general, if you just have some associative algebra, that isn't really a sensible notion because you have zero acting, so zero always acts with the zero trace. Yeah? So for the things that we're studying, it's just not a useful concept.
There was another question, so yes, please.
Yes, so I wanted to ask, is there some result on indecomposables? Is there a good notion of indecomposables for two representations, and is there something known about them?
Yes, in some sense, because you can define a direct sum on two representations. So then, but we haven't really studied. So I've looked a bit into sort of extensions of two representations. And then those extensions that we studied are definitely indecomposable, because otherwise they're not very interesting. But I mean, we're far away from classifying all indecomposables for anything like that.
Okay, we have time for one more short question. Yes, up there.
Well, thank you. So maybe not such a short question, but I will take the opportunity to ask anyway.
We'll make it short.
Okay. So I guess my question is more of a historical one. So you mentioned, you gave all these applications of categorification to representation theory, but maybe a major mission for our community, the category theory community, is to find ways in which category theory can make other aspects of math easier or introduce new theorems. So I'm interested in how people came to recognize that category theory would be useful in categorification.
Well, I mean, somehow when you look at these examples, they're naturally higher categories. Yeah. So it became obvious that we would at least need to learn about two categories and what those are and so on and so forth. And then I guess actually, so this finitary two representation theory, so Raphael Bouquet said something would be needed at some point in his two-category paper. But when I was visiting Mazurchuk in 2010, so our first paper actually grew out of us just trying to understand what the hell was going on and trying to write down some of the definitions, because I was constantly getting lost in categorical layers because I wasn't familiar with working with that. So we tried to write down some definitions, and then we came across these cell 2 representations, and then it turned. But I think it was sort of around that time. And okay, so what I should also say is that there are in parallel, people around Etikoff, Ostrich, so EGNO have this big book on tensor categories, and they were looking at different enrichment. So they enrich over a billion categories with certain, and so this sort of developed in parallel.
I think we have to leave it like that, and we thank Vanessa again for her talk.